All right, here we go. So we're going to do one more model. Oh, actually, first we're going to fill this in for a model. So a logistical model is the population after time t is given by this function. So here we go. It's c over 1 plus a times e to the negative bt, where a, b, and c are constants. A is greater than 0. C is greater than 0. The model is a growth model if b is greater than 0. So if your b, that's your rate, is greater than 0, it's a growth. And of course, if b is less than 0, then it's going to be a decay model. I'm going to do an example when we turn the page. Okay. So your domain of this type of function is going to be all real numbers. The range is the interval from 0 to C. C is something that we call the carrying capacity. C is like a limit. This function can approach C, but it's not going to actually touch C, which is why there's a parenthesis at the end of that C. It's called the carrying capacity. There are no x-intercepts. The y-intercept is whatever you get when you plug in a 0 to your function. There are two horizontal asymptotes. One is y equals 0, or the x-axis, and the other one is y equals c, which is again that carrying capacity. Just as I explained, it can't go anywhere above that. The function p of t is again increasing if b is greater than 0, and it's decreasing if b is less than 0. So it's a growth model or a decay model. There's a point of inflection where p of t equals half of the carrying capacity. The inflection point is the point on the graph where the graph changes from being curved upward to curved downward for a growth function, or where it goes vice versa for a decay function. And again, the graph is smooth and continuous with no corners or gaps. So remember, actually, the last time we had class, someone mentioned, and we hadn't had the word before, but this right here, if you look at the cubic function, that is a point of inflection. That is a point of inflection. It's where it goes from concave down to concave up, or vice versa. So that's what they talk about by point of inflection. All right, so here's our example that we're going to do here. There's going to be a lot of algebra, so let's get ready. So this type of wood product model classifies wood products according to their lifespan. There are 4 classifications. Short is a year, medium short is 4 years, medium long is 16 years, and long is 50 years. Based on data obtained from the European Forest Institute, the percentage of remaining wood products are T years for wood products with a long life, with long lifespans, such as those used in the building industry, because you want those to have obviously a long lifespan. And that function is given by this. Wow, look at that function. So the first question is, what is the decay rate? Well, the decay rate is going to be right there. Move it over 2 places, and it's about 5.8% per year. What is the percentage of remaining wood products after 10 years? So you would find P of 10, which again just means you're going to plug 10 in for T. I'm not going to show all of the work, as it's just something that you do in your calculator, but I will tell you that you get about 95%. So you lose about 55% of the product in the first 10 years. Now, notice all the space we have for C. There's a reason, and I'm going to show the math. How long does it take for the percentage of remaining wood products to reach 50%? So that 50 is my P of T. So I'm going to use my formula. I'm going to plug 50 into there, equals 100.3952 over 1 plus 0.0316 E to the 0.0581 t. So in all of that, we have the variable t. We're looking for time. So I just wanted to show you the steps to solving this equation because it can get a little bit ugly. The way I do it, the way I think it's the easiest, is to put a 1 in here and cross multiply. So when I cross multiply this way, I'm not going to distribute though. I'm going to leave it as 50 times 1 plus 0.0316 e to the 0.0581 t is equal to, and of course when I cross multiply that way, I'm going to get 100.3952. The next thing that you want to do is you want to divide both sides by that 50. So you're going to end up with 1 plus 0.0316 e to the 0.0581 t is equal to, when I divide over there by 50, I'm going to get 2.007904. Again, pause it when you need to. Now I'm solving for t. I'm going to subtract the 1. So now I'm going to have 0.0316 e to the 0.0581 t is equal to 1.007904. We're going to take the common log of both sides. Oh, actually, no, I lied. There's an e. We're going to take the natural log of both sides. Kind of got lost in there. This is going to come, oh, actually, nope. Remember, this is base of, what am I going to do? Oh, back it up. Sorry about this, guys. We need to do one other thing. You guys probably saw this. I just got lost in my math here. My apologies. We need to get this thing alone. So we have to go back and we have to divide both sides by 0.0316. That's going to give me e to the 0.0581 t is equal to, and when I divide this 1.007904 by this number, I get about 31.9. Sorry about that. Now I'm going to take the natural log of both sides. There was an extra number in there, and I couldn't figure out for a minute where it came from. Now remember, this is a base of e, so this turns into be 0.0581 t equals the natural log of 31.9. So now, to solve for t, we're just going to divide the natural log of 31.9 by this decimal, and we get approximately 60 years. It's a lot of work. And then for D, explain why the numerator given in the model is reasonable. Well, it's reasonable because it can't be any more than 100%. And that's pretty darn close to 100%. All right, there we go.